check this out. We've got something really fun today. This is so amazing. Oh man, again? 2.2, trigonometric ratios of angles in standard position and solving first-degree trigonometric equations. How do we find sine, cosine, and tangent of an angle that's larger than 90 degrees? We'll look at that. And how do we define sine, cosine, or tangent of a negative angle? We'll look at that too. First of all, let's start off with our angle in standard position. So we put the vertex here at the origin, and we can have any point on our Cartesian plane. We draw an arrow from the origin to that point, and we can create a triangle with those points there and going straight to the closest x-axis. And remember, we can use the Pythagorean theorem to find r or x or y if we're missing one of those and we have the other two. We want to write sine theta, cos theta, and tan theta in terms of x, y, and r from this image here. So sine is opposite. This would be our y value over hypotenuse. So y over r. Cos, the adjacent, which is our x value of this coordinate, over the hypotenuse. And tan is opposite over adjacent. Let's give that a try with the point -4, +3. So I'm just going to draw it first of all to get an image of what this looks like. So 1, 2, 3, 4, +3, 1, 2, 3. So there's my point on the graph. And that defines an angle in standard position. So we have a line going back to the origin, and this line here, and there is our angle theta. Now this angle in between here and here is our reference angle, so I could just make a note of that is our theta r for theta reference. This is my triangle here going straight back to my x-axis. We want to determine sine theta, cos theta, and tan theta. So this side length here is -4, and this side length here is 3. Let's find sine theta. That would be opposite 3 over the hypotenuse, which we need to find. So let's find it using the Pythagorean theorem. A squared plus b squared equals c squared, or 3 squared plus -4 squared. Make sure you square the negative so it will always go away. And we get that c is equal to ±5, but it's a linear measurement here, so we're only interested in the 5. So our hypotenuse for this right triangle is 5. So sine theta is 3 over 5. And cos theta is the adjacent, -4 over 5, and tan theta is opposite over adjacent, so 3 over -4. And maybe you want to write -3 over 4 like that instead. Now, just make a note that we never did find theta, and we didn't need to. Would the values of x, y, and r remain the same in all 4 quadrants if we had the same reference angle? Let's give this a sketch here to see what we're talking about. So there's our y-axis and there's our x-axis. And say we have a point in each one of these quadrants that gives us the same reference angle. So each one of these is theta r, and we're saying, are the values of x, y, and r going to be the same? Well, r is the measure of the hypotenuse of our triangle, so r would not change at all. But these points here would change. X is going to be positive here in quadrant 1 and 4. Let's see if we can color that in. And y would be, so x is positive here, and y would be positive in quadrants 1 and 2, because that's where the y values are positive, and these quadrants are where the x values are positive. So y values positive. So the x and y values will be different, but the absolute value of them will be the same because these are the same triangles, just reflected into different quadrants. They have the same reference angle, the same hypotenuse. So the x values will be the same for quadrant 1 and 4, and they'll be just the negative in quadrant 2 and 3. Create a chart that summarizes the signs of the trigonometric ratios in each quadrant. So remember the x value of our coordinate is cos, and the y value of our coordinate is sine. Let's see how that would look. It might look something like this. We've got cos is positive here in quadrant 1 and 4. Sine is positive here in quadrant 1 and 2. And tan is positive where sine and cos are both positive, or where sine and cos are both negative, because tan is sine divided by cos. So this is a lot to remember, and it might be easier just to remember which ones are positive in each quadrant, and then we'll know that the other ones are negative. So in the first quadrant here, they are all positive. In the next quadrant, it's only sine that's positive. In the next quadrant, it's only tan that's positive. And in the last one, only cos that's positive. Think of a strategy that you can create that will help you remember where each of the trigonometric ratios are positive and where they're negative. So we just saw in the last slide there that they're all positive here. Sine is positive here, tan is positive here, and cos is positive here. And so some people remember this using the cast rule because C-A-S-T spells cast. And this is to help us remember which are positive. Now, if you don't like cast, you can think of a more interesting way to remember this. We have Captain America smacked Thanos. We have Catherine Tran saves America, or all sober teacups. And you can make up your own. I'd love to hear it. Using your calculator, determine the following. And then we want to know how they're related and how they're different. So sine 30, if you put that in your calculator and you're in degree mode, you get 1/2. Put 150, sine 150 in there, you get 1/2 again. Sine 210, you get negative 1/2. And sine 330, you get negative 1/2. Now how are they the same? Well, the absolute value of each of these ratios is the same. Another important note is that they all have the same reference angle. So when we draw this out, we see that they all have a reference angle of 30 degrees. The first one is 30 degrees. The next one is 150 degrees, so that's in quadrant 2 with a reference angle of 30 degrees. Next one is 210, so that's 180 plus 30 degrees. And last one, 360 minus 30 is 330. So they all have the same reference angle. It's just some are positive and some are negative. But they're all using the same triangle, and so that's why all the ratios are going to be the same. Let's find the exact value of sine 240 degrees. First, let's sketch 240 degrees so we can see what it looks like. Here's our y and our x-axis. 240 is 180 plus 60, so something like this. And we'll just put our direction arrow on here so we can see where we went. Now that means that we have a reference angle of 60 degrees. Since we have a reference angle of 60 degrees, that means we can take this triangle that we created here and think of it as if it was in quadrant 1. And then we can say, hey, what is sine 60 degrees? And sine 60 degrees from our special triangle or from our unit circle, whatever you're using to memorize this, is root 3 over 2. Now, since this real angle, though, of 240 degrees is in quadrant 3, then sine is negative. So we take the same ratio here because it represents the same triangle, but in quadrant 3, it's going to be negative root 3 over 2. And that's because the hypotenuse is going to be the same, but the y value is going to be negative because it's down here below the x-axis. Let's look at example 4. We have a point -6, -4. So let's put that on our graph. -6, 1, 2, 3, 4, 5, 6 would be here on our x-axis, and -4 on our y-axis would be 1, 2, 3, 4. So somewhere down here is our point. And it defines an angle theta in standard position. So that would be going back here to the origin and starting at the positive x-axis. So this angle right here is our theta. Now we can't make a triangle with theta, but we can make a triangle with the reference angle, and so that's what we do. Make a right triangle here with our reference angle theta r. I don't know what theta r is, and it doesn't matter in this question. We're just trying to find sine theta and cos theta and tan theta. So let's see if we can do it. This side length right here is -4, and this side length here is -6. We're missing the hypotenuse, which we're going to need for both sine and cos. So let's find that using the Pythagorean theorem. So we got -4 squared plus -6 squared is equal to c squared. And that's 16 plus 36. And that's 52 equals c squared. And so c is just equal to the square root of 52. And we can make this into a mixed radical, which will help us reduce these ratios so that there is a perfect square of 4 in here. So the square root of 4 is 2. And if we divide 52 by 4, we get 13. So that's the hypotenuse, the length of the hypotenuse of our triangle here, 2 root 13. Now we got sine theta. Remember, we're using the reference angle here. So opposite is -4 over the hypotenuse is 2 root 13, which simplifies to -2 over root 13. We're using theta r, or the reference angle, because that's the angle that will make this right triangle. Theta itself is much too big to make a right triangle. It's over 180 degrees. Let's do cos theta, would be the adjacent over the hypotenuse, and that can also be simplified to -3 over root 13. And tan is opposite over adjacent, so it simplifies to 2 over 3. And you can see what's going on here. Sine is negative because this angle is in quadrant 3. Cos is also the same deal. And tan is positive because it's positive in quadrant 3. Point P is at K12, and it's 15 units from the origin. Point P lines on the terminal arm of an angle theta in standard position. And we know that theta is in between 0 and 360 degrees. So we want to find theta and sine, cos, and tan of theta. So let's find K, because that's a missing value there. And we got something like K is an unknown x, and then we do know the y value is 12. So that will be up there, somewhere here. There is our angle theta, and this is 15 degrees. So to find this x value here, it's just one side of our triangle. So we got a squared plus b squared equals c squared. We've got 12 squared plus k squared is equal to 15 squared. And we get that k squared here is 225 minus 144. So k squared is equal to 81, and we take the square root of both sides here, and we come up with k is equal to plus or minus 9. Now that's interesting. It gave us two k values. So the plus 9 obviously goes here, but that means that the minus 9 goes on this side over here. So there's going to be two different solutions here, one in quadrant 1 and one in quadrant 2. Let's do quadrant 1 first in blue. We've got sine theta is going to be equal to opposite over hypotenuse, and we can simplify that. Always simplify, even though it doesn't say in the question. So 4 over 5. Cos theta is equal to, how about adjacent over the hypotenuse? And we can simplify that. And tan theta is equal to opposite over adjacent. And we can simplify that, 4 over 3. Now that we have that information, we can actually go and find theta, even though that was part A of this question. So we could take, say, the first one here. Sine theta is equal to 4 over 5. We can take the sine inverse of both sides of the equation here. On the left side, its sine and sine inverse will cancel, just leaving us with theta. And on this side, sine inverse of 4 over 5 is about 53.13 degrees. Now let's find the solutions in quadrant 2. We've got sine theta is now going to be the same because sine is positive in both quadrants, and remember we're dealing with the same reference triangle here. So still 4 over 5. Cos is negative over here in quadrants 2 and 3, so same ratio, but this time negative. We could also get that from the diagram here. Adjacent is negative 9 over hypotenuse is 15, and that simplifies to negative 3 over 5. We've got tan. Tan is negative here, and we can see that because opposite over adjacent, and adjacent is negative. So it's negative 4 over 3. Now, to find theta, though, if we put this into our calculator, sine inverse of 4 over 5, it's going to give us this angle here again, and not this angle. But we know that this angle here is going to be the same. It has the same reference angle. So really, theta here is just 180 degrees minus the angle, the reference angle, the same angle as we had before. And we get that this is about 126.87 degrees. Quadrantal angles are when the terminal arm ends on the x or y axes. For example, 0 or 90 or 180 degrees. Let's see what would happen with sine, cos, and tan for each one of these quadrantal angles. Now for 0 degrees, we don't really see a triangle, and that's what confuses some people. So it's useful to just think of a triangle really close to 0, but not actually at 0. So this is what we're calling R. It's the hypotenuse of the triangle. And this would be the opposite side here, and this would be the adjacent side. So at 0 degrees, this is our theta right here. The opposite side shrinks to 0. And the radius, or the hypotenuse, stays the same, and the adjacent is now equal to the hypotenuse because this went to 0. So it's like just two equal lines here. That's why we've got whatever x value this is, and the opposite side is 0, or the y value of this coordinate is 0, because the height of this triangle is 0. And then we have that r equals x, because the adjacent side is x. So for our sine at 0, it's just 0 over r, or just 0. Next, let's do sine 90, and the same thing applies, but this time it's the other way. Our y value is the same as our r value, and our triangle squishes into essentially just a line here. But these two are equal, and so it's y over r, and they're the same, so they just equal 1. 180 degrees, well, this one's over here, same thing is happening. 0 over r is just 0. 270 degrees, it's just negative this time. R is the same, but it's negative, so negative 1. With cos, same things happen this time. This one's 1, this is 0, this is negative 1, and this is 0. Tan is opposite over adjacent, so when our theta is 0, it's 0 over x, and that would just be 0. For 90 degrees, though, we have a problem. It's y over x, and that can't happen, so this one is undefined. 180 degrees would be 0 again, 0 over x. And 270 degrees, again, undefined because we have y divided by 0, and that can't happen. Let's solve this simple equation. Sine theta is equal to 0.5, given that theta is in between 0 and 360 degrees. So let's see what we could do. First, algebraically, if we had this, we can take the sine inverse of both sides of this equation, and on this side, the sine inverse and the sine cancel out, and we're just left with theta. And on this side, we put this in our calculator, we will get 30 degrees. Now the trouble with just depending on the calculator, though, is that this isn't the only answer. This is the only answer the calculator will give us, but we need to remember our cast rule, or whatever you're going to call it. So sine is positive. Sine's ratio is positive in quadrant 1 and 2. So sine theta is greater than 0. So in both of those quadrants. Now we've got this answer from quadrant 1, it's 30 degrees. But there's also an answer here, and it has the same reference angle as this one. So this one is 30 degrees, and this reference angle right here is also 30 degrees. And so we can find this angle in standard position by taking 180 and then subtract the 30 degrees to get 150 degrees. And that's the other answer that your calculator is not going to give you. And that's why you really need to know these trigonometric rules. Okay, so 30 degrees and 150 are two answers that fit in this domain restriction. Now, if you were doing the unit circle and using the pattern that I've mentioned before, you could also do this. This one, remember, it goes 1, 2, 3, 1, 2, 3, and then we divide by 2 on each one of these, and then we take the square root of each one of these, and that's the pattern there. And then sine is the second value, so it would be this one. So that's 30, 45, and 60. And then same thing on this side. So these go down the other way, 1, 2, 3, 1, 2, 3, take the square root, divide by 2, and we can see that sine is also 1/2 right here and here. So 30 degrees and 150 degrees from your unit circle. Example 7 is similar. We've got sine theta now equals -1/√2. So if we used our calculator, we could take the sine inverse of both sides here, and we could find theta, or at least one value for theta. Sine inverse and sine cancel, and theta is equal to -45 degrees. Now you see the problem here is that our calculator is giving us -45 degrees, but we can't use that answer because our domain restriction says that 0 degrees is the smallest we can go. So let's just put negative 45 on here. Negative 45 would be this angle right here, from here to there. Now, we need the answers going from 0 to 360. And since sine theta is less than 0, so sine's ratio is negative, then we know that it's in quadrant 3 and quadrant 4. So we got the one in quadrant 4, we need one in quadrant 3. And then coming around here, angle in standard position, this one is 180 degrees plus 45. That would be our first answer. So 225 degrees. And then 360 minus 45. 360 minus 45 to get the other answer of 315 degrees. So there's two answers. Theta is equal to both of those. In the next question, we've got that cos theta is equal to negative 0.6753. We want to find theta here to the nearest tenth of a degree if it's in between 0 and 360 degrees. Now this time it's a decimal here, so we will not be finding this one on our unit circle if you were doing the questions that way. But this isn't a problem. We can find the first theta value by taking the cos inverse of both sides here. And the cos and cos inverse cancel here, and we're just left with theta. And cos inverse of this, this into our calculator, we get that it's 132.5 degrees. So 132.5 degrees is in quadrant 2. So let's draw this out. We know that cos's trig ratio is negative. So cos theta is less than 0. Therefore, theta is in quadrant 2 and quadrant 3. And we got this one, 132 degrees, somewhere there. Now to find the other answer in quadrant 3, it's going to have the same reference angle as this one. So we just need to find the reference angle. So theta reference is equal to 180 degrees minus 132.5. Then we can find this right here. And we get that that is 47.5 degrees. And then to find this angle here in quadrant 3, we just need to say 180 degrees will get us to here, plus the reference angle this time, plus 47.5 degrees. And we get that it's 227.5 degrees, and that's our answer in quadrant 3. So theta is equal to both of those quadrant 2 and quadrant 3 answers. Now we'll solve these trigonometric equations. They still have the same domain restriction, 0 to 360 degrees. Looks like here we can divide both sides by 2, and then we get that cos theta is equal to 1/2. Now if cos theta is greater than 0, it means that our answers are in quadrant 1 and quadrant 4. So let's go find this. We can take the cos inverse of both sides here, and I'll just write it on this side. Cos inverse, and the calculator gives us 60 degrees. And that's our answer in quadrant 1. And our answer in quadrant 4, remember, it has the same reference angle. So it's in quadrant 4, but it has a reference angle of 60 degrees. So we can find that by going 360 and then going back 60. So 360 minus 60 gives us 300 degrees. So there's our two answers for theta. Next one, we'll have to do a bit more algebra, minus root 3 on both sides. So 2 sine theta is equal to negative root 3. Divide by 2 on both sides, and we get that sine theta is equal to negative root 3 over 2. Now, sine trig ratio is negative, so sine theta is less than 0. Therefore, theta is in quadrant 3 and quadrant 4, so below the x-axis. So let's do this in our calculator. We take the the sine inverse, of both sides here, and we get that theta is equal to negative 60 degrees. Now we can't use negative 60 degrees because that's outside our domain restriction. So we can put that on a picture though, and it looks like this. So 60 degrees is actually our reference angle here, and it's happening in quadrant 3 as well. So this is also reference angle of 60 degrees. So our theta is equal to, this one's 180 plus 60 is 240 degrees. And this one here is 360 minus 60 to get back here, and that would be 300 degrees. This was part of Trigonometry 1 and 2, understanding angles in standard position, and also solving problems and equations using sine, cos, and tan. Here's some questions from the textbook. Try them out. See if you know what you're doing.